Hi, so this is a video about how to extract signal from raw electrochemical data. So at Zimmer and Peacock, we're focused on electrochemical sensors and electrochemical biosensors. And I'm going to use the example of cyclovoltammetry. Now, if you're not sure what cyclovoltammetry is, then on our YouTube channel, there'll be plenty of videos around cyclovoltammetry, but you don't need to know what cyclovoltammetry is in order to follow this video. Cyclovoltammetry basically gives us raw signal. So we have a raw signal from a set of experiments, and we might have been changing a parameter like concentration, or a changing parameter could be time, for example. But we have a series of raw data, and we might have to correct that raw data. So in the case of cyclovoltammetry, we might want to measure the height of a peak relative to a baseline. Now, in electrochemistry, sometimes the baselines are flat, sometimes they tilt, and sometimes they move from experiment to experiment. And so it's, you actually have to basically sort of be aware of it and know how to do an extrapolation from a region and create the baseline. So sometimes, you can't just take the absolute peak height, you have to take it relative to a baseline. And if the baseline is shifting, you have to know about it and compensate for it. So the message here is we gather raw data, and sometimes we have to correct the raw data. Now, after that, then we have to look for features in the raw data which are indicative of the analyte of interest. So, for example, if using cyclovoltammetry, the peak height is often proportional to the concentration of the analyte of interest, so that's good. But also the peak position is proportional to the analyte of interest. So you might have a signal or concentration that is proportional to feature 1, let's say the peak position along the x-axis and the peak height along the y-axis. So I have a simple equation here, which is signal or concentration is equal to feature 1 plus 2 times feature 2. The equations are never that simple, and I just want to kind of comment upon that a little bit, that at Zimmer and Peacock, we have almost a workflow where we have laboratories which are, the scientists are in there are generating data, they're uploading it to a cloud database. So there's a guy gathering data, for example, there's another guy who maintains an online database which can do analysis in that database. But then we have other guys who might be doing data cleanup, and other guys then who might be downloading that cleaned up data and actually doing analysis on it using MATLAB or JUMP or Python scripting. So there's a data generator, there's somebody generating data, there's somebody maintaining databases, there might be somebody doing cleanup, and there might be somebody doing data analysis. So there's at least in our data analysis group, there might be 4 people involved in the overall process. So I just want to kind of comment that Excel really won't cut it. I mean, Excel is an accounting tool. It's a cool bit of software. It's quite ubiquitous, but Excel really won't cut it. If you want to get a decent and if you want a decent algorithm, let's say for extracting signal from your features, then you need to be more sophisticated in your analysis. And it brings me to my final comment here, which is these days, people are very interested in doing continuous monitoring of something. So, for example, let's say my signal was the pH in some sort of food production, and the pH changed as a function of time. Now, I could have 2 sensors, and I've shown it here as in green and red. Now, the 2 sensors with their absolute signal give different absolute signals, but they're, in this example, they're modeling the same process, so they should really not be they should definitely not be different, but they are different. It's because the sensors themselves are different, or they're in slightly different environments within the food, but they're different. So in that kind of situation, one fix is to actually not show absolute signal, but think about relative signal. So for example, in this data, there's a flat region, which is the kind of initial baseline, and then the signal takes off and then it plateaus again. So if you change into a relative mode where you say, okay, well, what I'm going to do is I'm going to express all my data relative to the flat region, then what that should do is take care of the sensor variability and actually leave you with just the true signal from the analyte of interest. So that's just one of our strategies, let's say, to get rid of sensor to sensor variability or experiment to experiment variability. So let me just summarize and say, okay, so you can gather electrochemical data. You might have to correct that electrochemical data. You might have to identify features in that electrochemical data that are proportional to the analyte of interest. And you might have to be quite sophisticated in that feature extraction. And if you are relying on Excel, then it's not going to be powerful enough. And you do have to get onto MATLAB, Python scripting or coding, also jump from SAS. And then finally, this is just a specific case that comes up quite a bit, that people want to do continuous monitoring of an analyte of interest, and two sensors might give them slightly different absolute signals, which you can either fix by doing a 1-point or 2-point calibration, or in fact you could show relative signal, where you can show relative changes by using, like, say, you use some initial data points as your baseline, and then you show everything relative to the baseline after that. So if you have any questions about Zimmer and Peacock, I'll put a contacts link on the YouTube channel. Okay, thanks very much.